Hello, and welcome to this video. In this video, we're going to be looking at the energy changes that take place in a gravitational field. So we've already looked at the forces that occur in gravitational fields due to the gravitational field strength. We then looked at the gravitational field strength and said that this is an effect of the force per unit mass on any test mass that's in the gravitational field. We then related that to a scalar potential value. So we could say that any point within a gravitational field will have a single scalar potential value. But then we said we had these things called equipotential lines. And we also specified that we can move between these equipotential lines. But when we do that, we're changing the potential, okay, which means we have a potential difference. And we've defined in electricity another kind of potential difference, which is not the same because that would be electrical potential difference, but if we have gravitational potential difference, it's still a measure or related to a measure of energy. So if we first then see that we have the type of energy we have is gravitational potential energy, right? So there has to be some gravitational potential energy in a field, okay? Because if we go to the surface, so if we then look at a uniform example of this, we've always known the equation that the gravitational potential energy is just m times g times h, where m is the mass of the object, g is we used to call it the gravitational acceleration, now we're going to call it the gravitational field strength. So this is the field strength, and h is just the distance from the ground that it is, okay? So the distance from your starting point. Now we're going to use this same idea and say we can apply the same kind of theory the same way we applied F equals ma to the gravitational potential energy. So in a radial field, we're going to start with this gravitational potential energy is, and we'll start with just g, right? And we know we define g to be gm over r squared, but now we're going to times it by the mass, m, and then we're going to times it by the distance, but in this case we're calling it r. So if I times by r up here, I'm just cancelling out those r's there. So I end up with an expression that is the gravitational potential energy in a radial field is gm m over r. Now I'm going to put this in a double box because this isn't on your formula sheet, but you can be asked about the changes in gravitational potential energy. And the way they do this is not to ask you about this formula, they ask you more about a formula for the work done. But what we can see, the reason that we can say that the potential is related to the potential energy is because if I write again an expression for potential over here, so potential we said V is minus Gm over R, okay? Now the key with this then is to say that, well, this potential, in order to get from the potential to the gravitational potential energy, I'm just multiplying by this m. That's the only difference between these two, along with the negative sign. But this, we said we have to define it to be negative for this to work. If we just look at the magnitude of the energy, then it's just a positive value. But it is possible to get negative gravitational potential energy. So as a general rule, kinetic energy, thermal energy, those kinds of energies can't be negative, but potential energies can be negative. So I'll put that as a side note down here. So potential energies can be negative. Okay, and that's just because if our potential starts off being negative and we're multiplying by a positive mass, we're always going to get a negative potential energy. Okay, so this means that actually I can write the potential energy as GPE is just m times v, right? I'm just going to have the mass multiplied by the potential. So we can think about it this way, but there's a similar equation to this on the formula sheet, but it's actually not looking just at the potential energy, it's looking at the work done. So we have to first remember what is the work done. Well, we said work done is just an energy transfer. Okay, so the work done is just going to be representing the amount of energy required to change the potential acting on a test mass. Okay, so we're saying if we go to this argument that we had before, where we have some sort of point mass and we have these equipotential lines based on its radial field, if I wanted to change the potential, I have to move either towards or away from the mass. And so that means that I have to either put in energy, so I have to transfer energy to accelerate away from the force, so in the opposite direction. So if it was Earth, for example, in order to get out of Earth, we need a rocket with loads of fuel in order to propel you out of that gravitational field. And if you wanted to come down to this gravitational field, you also have to put in some amount of energy, although there's a little bit more complication with that, since you're gonna you'd have more of an energy transfer, since you've started with quite a high value of potential energy. The further away you get and the closer you get, you have to conserve energy. It just means if you come closer, it will be converted into kinetic energy, so you're going to start orbiting this faster. You can think about it in terms of the sun. Mercury, we know, has a 1 year on Mercury is like 97 days or something like that, because as you get closer to the sun, it begins to orbit the sun much faster, because you have a stronger force, and the total amount of potential energy has gone mostly into kinetic energy by this point. Okay, so now we need to come up with an expression on the work done in order to move between two potentials. And in order to do that, we just say that the work done, W, must be equal to the mass, and what we're saying is we have a change in potential here, so it's the mass multiplied by the change in potential, and this is on your formula sheet. So if you have trouble remembering formulas like this and being able to understand where they come from, you can always look at this formula and say, okay, in order to get to an energy, I have to multiply a potential by the mass. You just get your potential equation, which is also on the formula sheet, and then just multiply by the mass of whatever object is there. Now, what I would say is that this work done, what we're going to assume is that it always has to be positive for when you're escaping the field. So if you want to get away from Earth, you then have to put in energy, so the amount of work done will be positive. And you can see this because if you have a change in potential and you're going away, your final potential, so VF, so I could also write this, if you wanted to, as W is M times the final potential that you get to minus the initial potential that you start at. Now, if you're moving away, the final potential is bigger than the initial potential, so that means that this is a positive number, so you'll end up with a positive work done. If you're ending up moving towards it, your work done can be negative, okay? So that means that my initial potential is smaller than my, my initial potential is bigger than my final potential because I'm getting closer. So that means that this is then going to be a negative number, which means that actually my work done will be negative. So the work done, because it's the energy transferred, you can both lose or gain energy. So work done can also be positive or negative. Okay, depending on which direction that you're moving in. Now, questions about work done will usually give you equipotential lines, and they will say, in order for this rocket or this satellite or this object to move from this potential line where the potential is minus 30 joules per kilogram, for example, and then to get up to this point where your potential is minus 15 joules per kilogram, how much energy would be required? And then you would just simply take the difference between those two potentials by doing this final potential minus the initial potential, multiply it by the mass of that satellite or object, and then it will give you your work done. Now, I do recommend that you try to learn this equation, since this is also going to pop up in another equation that we're going to derive in a future video for the escape velocity. And so I would say the key that you need to understand is in this gravitational field, it's basically identical to gravitational fields in a uniform field. We still have the main differences between kinetic energy and gravitational potential energy. We're just going to convert between the two. If you get closer to the surface, it means you're losing gravitational potential energy, you're gaining kinetic energy. If you move away from the surface, you're losing kinetic energy, you're gaining gravitational potential energy. So it works exactly the same. We just have a few different formulas and ways of representing it. So hopefully this all makes sense, and the energy changes in a gravitational field are okay. Thank you for watching.